This conference will now be recorded.
So good afternoon everyone and welcome to our latest SCLF webinar, and I'm delighted to welcome WIll Fardon, today from I2 Analytical, but I'll properly introduce him in a wee minute. We'll just do some housekeeping. Anybody that doesn't know me, I'm Alison Mackay, I'm a member of the SCLF Executive Committee, and I'm your host for today. I will be keeping a wee eye on the chat, which you can use to either have a chat with other delegates that are here, or to ask questions in the chat. We will have some time for questions at the end, so you can either put them in there and I'll be monitoring it, or you can unmute yourself when we get to that part of the session. And as I said, that part of the session won't be recorded, so it allows for any discussion that wants to take place. You will have arrived on mute, so if you can just try and stay on mute while we're actually doing the presentation, it just avoids excessive feedback. That would be great. And I've also put in the chat there Will's nominated charity, which is the Archie Foundation, which is a charity for 6 children. I think it's based in Dundee, but they work across Teesside, Grampian and the Highlands. So if you're able to make any donation to that, that would be much appreciated. In terms of our next webinar, our next one is going to be in 2 weeks' time, at the moment anyway, and it will be an introduction to the construction waste portal by John Logan. So I'll be sending out details for that probably at the beginning of next week. We are obviously looking for any suggestions for future webinars. If you want to present maybe a case study or whatever, if you just get in touch with myself or any of the other members of the executive committee, and we'll make it happen basically. So I think that was all from now. Oh, the other ones that we've probably got coming up is maybe 1 or 2 on water sampling. We're hoping that someone from SEPA will be able to do that. It might go over 2 separate webinars, one in groundwater, one in surface water. So they're just working that out. We'll try and get some dates in the diary for that too. So without further ado, I'll introduce Will. So Will's Senior Technical Manager at I2 Analytical, and has spent all of this century and a bit of the last working in various analytical laboratories in the environmental and pharmaceutical sectors. So he's got plenty of experience that I hope you, like me, are looking forward to hearing from today. So I'll just hand over to you, Will. Thanks.
Okay, thank you very much, and hello to everybody. I'll just crack on, I think. So what I'm going to try and look at over the course of today is sort of an end-to-end element of basic laboratory activities. I've tried to make this as generic as possible, but I can't promise there won't be a little bit of I2 product placement dotted around through the place. But I've tried to make it so that we're looking at general laboratory procedures and activities rather than things specific to I2 as a lab in itself. So we'll start looking at some basic sampling requirements. I'm not going to go through the whys and wherefores best practice of sampling, just things that have impact upon the lab and our ability to perform the testing going forward. That leads into one of the most commonly asked questions that we get in labs is, why all the different containers? Why do you need the different pots? Why all these different bottles? What's the point? Which then leads us very nicely into sample deviations and some of the guidance behind that, what it really means and how it affects your work. The accreditation, I've actually moved this to the back end just because I'm aware of the amount of time that I'm going to spend talking about some of the earlier elements. So the accreditation is kind of a bit of an optional extra. So if we get to the end of everything else and everybody's still awake and doesn't have real work to do, we can dip into that in a little bit more detail. Slightly facetious title of the importance of penmanship, looking at sample submissions and the practice of getting samples from the client into the lab and then getting them processed in a timely fashion. What kind of things happen in the lab? Just a brief summary of some of the main types of analysis. And throughout all this, I'll be looking to try and flag up any specific areas where we've known issues and things to look out for in the process, anything that we can do from your side or from the lab side to make the process a lot easier and smoother. I will point out most of these individual headings I could probably do about 45 minutes on individually, so some of them may feel a little bit brief If there's any questions, if there's any of these elements that you want more details on, then obviously anything we can cover in the questions at the end, that's great. But if you'd like to spend a full 45 minutes listening to me talk about the TPS 63 guidance for sample deviation codes, then please contact me outside of the meeting and we'll look to arrange something that we can do directly. Moving on. So to start off, weirdly for a chemist, looking at geotechnical testing. So at IT, we do both chemical and geotechnical testing, but in this respect, this will apply to any geotechnical lab that you're looking to submit samples to. So some of these may seem blindingly obvious, but are things that cause us potential issues and occur fairly frequently in the real world. Make sure we get enough sample. I'll come to a slide in a couple of time now, just detailing just some of this, just how much sample we need to perform some of the basic tasks in the geotechnical lab. Making sure that sample is being utilised to the full. What we sometimes get is, I want to do a compaction, I want to do some PSDs, I'll send in effectively separate samples for both. But look at where we can do more work from a single submission, make it as efficient as possible. Make sure you're scheduling your testing on the appropriate sample submission. Some types of testing can be done on a disturbed sample, some on a window sample, some on the U100, but others is quite specific as to what can and can't be done, and make sure you're taking the right type of sample for the testing you want. And make sure everything's labelled appropriately so we know what it is and where it came from. Everything that we do in the geotechnical lab is very, very tightly controlled in terms of working to British standards. So we have everything historically, well, the majority of things working to BS 1377, a lot of things new moving on to the new EN Euro Code 17892. Making sure that we have the appropriate testing instructions prior to us starting. Generally speaking, we're not going to start doing anything until we've got all the right information. And what we're looking to try and avoid is delays. So where we get partial information, we can't look to proceed until we've got everything that we need. And a prime example would be things like shear box and triaxles. It's not just a case of picking off a shelf, right, I'll have a shear box, please. We need the test pressures that you need us to operate that test at before we can proceed. Similarly, including any remolding instructions for CBRs, and where there are varying options within a test, make sure that you're specifying exactly what you need. And if you're not sure, then we've got your lab, and ours included, will have technical specialists in that business who can advise and instruct and help you narrow down that. Sample volumes, as a rule, the more granular the material, the more of it we need. Making sure you're always looking to take bulk or multiple bulks if you're undertaking earthwork testings. Certain types of sample, so the EU and UT samples for undisturbed triaxles and odometer tests, window samples not suitable for use for undisturbed tests, and just the awareness that classification testing can be undertaken on samples with other things. And just to try and put that into a little bit of context for some of this, these are some of the more basic and commonly requested geotechnical tests that we do. So even something as basic as a moisture content. If we have a finely ground material, we need 50 grams of that. There is no point in sending us a bulk bag of 25 kilos. It's a waste in terms of the time for sampling, it's a waste of the logistics for shipping it there, and it induced costs for disposal. However, if you've got quite a coarse aggregate material, then we would need 4 kilograms. These become slightly more exaggerated as we get into things like compaction testings, where we're up to sort of 50 to 80 kilograms, depending on sort of the particle size of the material. If in doubt, ask the lab. What we'd look to try and avoid is either we have too little, and then which means we either can't complete the testing or you're back out on site, or we have too much, which just causes problems from end to end, from an environmental, from a logistics, from a cost, disposal. We look to try and avoid that wherever we can. And as you'll see from the bottom, there are some tests that are suitable from all different types of sampling mechanisms. So a small disturbed sample, or a tub, for want of a better word, a large disturbed samples, bulk bag, then you have your undisturbed samples, U70s, U100s, core samples, or then window samples. But not all testing is applicable for all sampling types. Again, if in doubt, speak to your lab. Right, back on more familiar ground here, environmental testing. So The premise is you guys are out there in the field taking samples, and you've got to get them to us in as close to the original condition as possible. So what we test is as representative as possible of what you've dug out the ground, taken out a stockpile, fished out of a river, whatever the mass sampling mechanism is. It needs to get to us in a condition. So when we test it, what we're testing is as representative of what you've taken as we can get. So you make sure we're using appropriate sample containers. Generally speaking, soils particularly, most labs in the UK have pretty much standardized now on a plastic pot and different size glass jars. But whichever lab you're working with, they will be able to give you specific instructions as to which containers, are the most suitable for the particular type of analysis you're taking at any given time. Try to avoid falling back onto, if in doubt, generically, oh, I'll just fill this, this will do. It's always worth just a quick question, a quick email, a quick phone call to the lab just to make sure. Making sure that we've got samples shipped and received to the laboratory in an appropriate time frame. Get them, basically, any lab will tell you, get them to us as quickly as humanly possible. Once you start adding extra time into the issue, then we start looking at bigger issues of stability of temperature and the environment in which it's stored. We can resolve and mitigate for most of these by, as soon as you take that sample, we arrange the logistics of that so it gets to us as quickly as we can. Keeping samples cool, so where laboratories provide cool boxes, insulated Corex plastic boxes. I know for water samples at I2 we have something called an environmental sample kit, which is basically black Corex box with very thick molded polystyrene inserts designed to be as thermally insulating as possible. Different labs will have different solutions to the problem, but ultimately the labs can provide help with this to make sure that you can get that sample to us and try and maintain the appropriate temperature, which as a rule is cold. In winter, all is good. This time of year, a little bit more difficult. And as I say, the lab that you're using is the best place to ask for exactly what is required on any given piece of analysis. Because all labs will differ slightly. They'll generally look ballpark the same, but there will be slight differences. Different labs will have validated different methods using a specific type of container, particular material, particular lid, a particular liner in the top of the lid. If you're used to working with the same lab on a regular basis, you'll become very familiar with what they use, and it all is nice and easy. If you're moving between labs, then it may be a little bit more difficult because what might be suitable for one will not necessarily be suitable for another. And if you ever want to check just to see the effectiveness of how things are working, then any lab can provide you with QA options such as matrix spikes, trip blanks, so samples that we can effectively send out to you with your empty containers that go pass through the whole sampling process, be exposed to the same environmental conditions, and you can look at the effectiveness of the process. Filling in samples, make sure everything's filled as much as possible with minimum headspace, particularly when you're looking at volatile organics. I think most labs now in soils use a 60-gram jar, and they fairly typically use the 40 ml EPA vial. They will have specific liners in the top, because if you're filling without headspace, you're going to have a lot of direct contact with the sample material, and you don't want any transfer of plasticizers or any other organic material into your sample. Try and take the sample as representative as possible. Again, I'm not going to go massively into sampling as a process, but if you've got 2.5 tons worth of fairly homogeneous muck and then 2 bricks in the top, don't send us the bricks, because that's not the results that we provide. We will just analyze what you send us. We will crush it, we will prep it, and we will test it, but that's not going to be representative of what you're actually interested in. And if you are testing, quite a lot of what we do where there's no volatile elements to it, we may look to dry the sample, because that makes it easier to then prepare and homogenize to make the subsamples that we ultimately use more representative. But some things need to be done wet. Great, if it is, we will just take the sample directly, but anything we dry, obviously we're discounting that moisture content. So if you're going out to site and you have a soil and it's incredibly wet, we need minimum mass values of dried soil, so we have to be able to discount the water content. So if you sample I was going to swear then, I'm not, very, very wet, then make sure it's worthwhile taking some additional sample material. Labelling of jars. We're coming up to our first picture round in a moment. Ultimately, we need enough information to identify the sample. It needs to be clear, consistent, and match up to the chain of custody. Because what we're trying to avoid is delays. If we receive something and we can't see what it is and easily identify it, match it up to the chain of custody, identify it to the client, because certainly at I2 we process anywhere between sort of 13 to 1700 samples a day, and that's a lot. Bearing in mind most soil samples will consist of 2 to 3 jars. That's a lot of jars, a lot of pots, which all ultimately have to be manually sorted. You can put all the automation in the world, but someone's going to have to take the lid off that and take the soil out of it. There is always a manual element, and anything that can be done to make it easier and clearer for us to identify that will mean we can get the samples in the lab quicker, which avoids delays, which then avoids potential for deviations for holding time breach. Now, the names have been covered off to protect the innocent on this one a little bit. These are some samples that were received probably a couple of years ago now. And it's probably a problem that will face most people either already or something they will face when they're out and about in suboptimal weather conditions. The jars are filthy. A lot of the text has been obscured by the mud that's on there, and the text that isn't looks like it's been written by someone with the wrong hand whilst riding a roller coaster. Now, if that submission was purely 3 samples and we had clear paperwork, it's 5–10 minutes of someone's time to go through and by process of deduction figure out what's that. But if that's part of a submission of 100 samples, that's a couple of hours while somebody figures that out. Ultimately, it may result in a phone call or an email back to you as a client. If you're on site, you're not available. And this sounds like a joke, but it happens more frequently than you'd probably imagine. We received that on a Friday. We ring them up and they go, oh no, sorry, that was the last thing. They've gone on holiday for 2 weeks and there's no one else here who knows what they were doing. It's just, again, it's more delays and it stops the samples getting into the lab and stops you getting your results. Equally adds extra potential for deviations. So try as best as possible to be as clear on the labels as you can. So what else goes into that box other than samples? Ideally, if it's available at the time, chain of custody with all the sampling information, all the project information, contact information, and testing requirements. But obviously appreciate, depending on circumstance, that testing requirement might not necessarily be available at the point where you're looking to send the samples back to the lab. So if we at least have some form of sample log sheet, a partial chain of custody, so we at least know what we're getting, the contact information for where it's come from. So if there are questions, we know who to call, we know who to email. And if we're expecting an electronic chain of custody being sent through at a later date, we know where to try and match it up to. Because ultimately, we're just trying to match one piece of information with information on the jars so that we can schedule appropriately and make sure that you're getting the right testing on those samples. Picture round number 2. What not to put in the jars, in the boxes, sorry. If you can help it, try to avoid ripped up, half-eaten, chewed by the dog, left in a puddle chain of custody documents because they're quite difficult to read. On this example here, we've also got people sampling waste. Now, we appreciate if you're at a remote site and you've got gloves, you may have filtering equipment, syringes, filters, other bits of sampling kit that you use. You're not necessarily going to carry a wheelie bin with you. And we are understanding of that, but for preference, we prefer not to receive people's waste. It means we have to take extra precautions when we're handling, and it just slows things down. Other options for this, what we've got at the moment, the traditional solution is a chain of custody. Obviously, these are I2 ones, but if you put your thumb over the top left-hand corner of that chain of custody, it will look like every one from any lab you've ever used. Because at some point, God knows how many years ago, some clever sod invented that and everybody's just stolen it ever since. So they're all very, very, very similar. And then we've got a jar with a label on. As technology improves and the world becomes increasingly more mobile device oriented, we can use towards other solutions such as the use of barcodes, QR barcodes in identifying samples. So going away from the bit of paper and label solution to providing sample containers with barcodes on, completing all your on-site information through an app or a bespoke system. I know Kinetics provide systems on the key logbook, and several labs, including us, can provide mobile apps that you can download to your phone, where you can complete that information, use the camera function of your phone, scan the barcodes, and that's the process of linking your sample jars to your sample information. And then that means we can make use of electronic data transfer from there on in, and we remove the requirement to have the soggy, dog-eaten, half-torn bits of chain of custody in the box entirely. Why? Why is any of this important? And the reason is deviating samples, something I'm sure everybody is very much aware of. This came into the world in about 2006, if memory serves. In the dark days prior to this being included within the accreditation scope, you could theoretically go out, take a water sample in a bottle that you bought from the local co-op that until recently had Coca-Cola in it, but you just poured down the drain just because you needed an empty bottle, filled it full of water, left it in the back of your car, forgot about it, gone on holiday for 2 weeks, come back, realise you've got to do another monitoring round, go and take a proper sample in a lab provided sample container with appropriate preservatives, fixatives, all the rest of it, and then submit the two samples together. The lab would process them both as received using an appropriate UCAS or MCERT accredited analysis, and on your report you would get two sets of results, and there will be nothing on there to distinguish between the two. This was, well, something happened in, I think it was in the Netherlands originally. A company over there instigated an exercise where they took varying different VOC samples in differing sample containers, some with headspace, some without, stored at different temperatures, and submitted them blind to different labs across Europe, who all provided reports, who all provided a UCAS accredited results, and they were all massively different. And this has sort of galvanized the world into, well, we need to add something into the laboratory process to be able to identify where there is potential risk that those results may not be truly representative of the sample material at the point of sampling. And this is ultimately where deviating samples come from and what it's there to do. It sometimes makes life a bit more difficult, but it is a force for good, if somewhat a pain in the arse at times. So it is included, and part of the requirement of ISO 17025, there is UCAS TPS 63 guidance document, which was issued to labs to give a little bit more detail of what they need to do. There is an awful lot of other information out there relating to this, some of it from documents such as ISO 5667. I've got the 2003 one that was updated last year, I should update that, and varying other British, European, and even US EPA standards relating primarily to sample stability and how different chemicals and different analytes behave in different matrices, different media, if exposed to different conditions and over time. Also, each laboratory and every lab is slightly different in this, all working to the same principle, but we'll be looking to validate their methods. Historically, we'd look to do to make sure we're getting an appropriate LOD, making sure we're getting consistent, repeatable results. But we also now look at how stable that analysis is. So a lot of information we can take from published standards, but labs will also be looking to define their own, because there's some variability within the analysis, there's slight variability within the sample containers. So you look to make it as close to your own process as possible. So again, a bit more IT product placement here. So for us, we have specific containers for our VOCs, the volatile hydrocarbon fractions, so use less than C10 TPH, BTEX, volatile fatty acids, a selection of anything that's done basically by Headspace GCMS. For that, for soils, we have a specific 60 ml per glass jar. Within there is a PTFE seal that we have used basically to start to finish, so the sampling into those jars and the analysis then completed from soil from those jars, so then we can confidently say that any sample taken in that particular container we are confident that it is stable for a period of time, rather than resorting to published standards, which is, I think, in 5667 for VOCs in soil, it's 4 days, whereas we have a stability period of 7, because we've specifically validated it in that container. These are all put out to UCAS. Again, this is not I2 specific, this is a lab thing. We will look to validate your own process. You submit it to UCAS, who will check and verify all the data, and once that's approved, then you can then put that back into your operating practice and use that as an operating standard for the stability time for those tests. So what out the back end of this is any samples that you submit, the lab will perform a series of assessments, and you will potentially get some form of comment on the report. Unless somebody out there, other than us, is being a little bit more fanciful, you generally won't get it on a little scroll. It will be a coded comment on the back of your report somewhere. But the things that we're looking against is, have we been provided with a sampling date? If we haven't, then we can't assess whether or not those samples are within holding time. As the commencement of the analysis exceeded the preservation or holding time. Is that because the samples were received past the holding times? Has there been issues in the lab? A couple of things could contribute, but ultimately the deviation is the same. Some of the bits of guidance from UCAS are a little bit vague. So has the sample been appropriately cared for? So this will cover things, some of the bits mentioned before, the temperature of storage conditions, which is a really difficult one to manage. And if anyone wants to talk more about that, that's a good hour-long presentation in itself. The appropriate headspace, so certain tests need to be submitted in sample bottles without an air gap in there, because that will affect the analysis, VOCs being the most obvious one. But there are various inorganic tests as well, which are better if submitted in a bottle that's completely full without air. Exposure to light, humidity, some chemicals are photosensitive, pH is for one, but if you put those in an amber glass container, that solves a problem. Is that sample container appropriate? Again, these days, most people, 99% of the time, will submit samples in containers that have been issued by the lab, who is going to ultimately perform the analysis, which is great because we can control that, and so there shouldn't be any issues. Anyone who's worked in labs since pre-2006 will have their own versions of this story, but I once received a soil sample in an empty packet of ready salted Walker's crisps. At the point that time, there was nothing for us to be able to, we could ring the client and say, are you sure? But necessity being the mother of invention, they were out, they needed to take a sample, they didn't have anything to hand, they had a bag of crisps in the car, they ate the crisps, shook it out as best as possible, filled it in. There's nothing that we could reasonably put on the report to highlight that. And so they will get a report at the back end of it that said, here's your UCAS accredited, MCERTS accredited results. We now have the means to be able to comment on that. I think one of the biggest misunderstandings, and again, this is a lot better now because we're used to dealing with deviations for 14 years now, is a deviation code is not somebody telling you your result is wrong. It is saying that there is something that has happened in the lifetime of that sample prior to analysis which may have had an effect upon the result. We can't quantify what that effect will be. If you just use, for example, the stability times, in order for us to be able to comment on that, we would have had a matrix that was identical to that which you submitted for that particular one sample, which may have been taken from a river at that one point and will be unique in itself, and then run in basically studies on that one to look at the degrading effects on the results over time. And that's just one sample material for one determinant. There are, I would say at this point, infinite numbers of possibilities of what could happen to that sample, and it's not possible for us to be able to map them all out. So all that we can say is that something may have happened to that sample. Now, there are some bodies, certain groups to whom you'd be submitting samples who will see deviations as a, well, it's wrong then, isn't it? Or it suggests a lack of confidence from the lab in the data. But that's something that you can discuss with the lab people, with the quality people there, because we have no choice. This isn't something that we decide to put on. This is something that we have a fixed series of criteria and we have to apply when the situation arises. But it doesn't necessarily mean that everything goes in the bin. Right, we're now in the lab. We have our samples, we processed, we scheduled, everything's on the LIMS database and it goes into the lab. And we're into analytical chemistry territory. So a scientific discipline that develops and applies methods, instruments and strategies to obtain information on the composition and nature of matter in space and time. How to turn dirt into numbers on a PDF, short version. So we've got varying different analytical methods. Generally speaking, a lot of things now, most things that are done routinely are based on very established techniques that will be derived from standardized methods. So we have British standards, European standards, EPA standards, there's national grid standards, there's the SCA Blue Books. We have methods instituted by HSG. There are varying standards out there from which we can look at and define methods. What you'll find, most labs will have the ubiquitous term of in-house method based on, because there will be an initial core of, right, this is an available standard that shows you how to analyze for X compound in Y matrix, but the context in which you're applying it in the lab is slightly different. So the lab will take information from that standard and then they will develop and validate something which is based on that information, but more specific to the particular requirements of the business at the time. Now we get a lot of queries, or I get a lot of queries saying, is this method compliant with this standard? And in the geotechnical world, it is, because there's no deviations. It is what it is. The standards are the methods and they have to be compliant. There are certain circumstances in chemistry, asbestos testing for one, has to be compliant with HSG 248. You have to be compliant with the UCAS Lab 30 document. But in a lot of other areas, you'll find a lot of methods that are based in and around established methodologies, but ultimately adapted over time. As an example, you look at something like pesticides. There may be a standard Blue Book method for that, which is incorporated into a lab, but then a client asks for, okay, can I have this additional pesticide included? Okay, so using the existing extraction process, instrument techniques, but you then spike in some standards for its new pesticide, everything works, you run through the validation, you submit it to UCAS, they're happy that it works all right. You've now got a method that was based on that original standard, but you have adapted it to include new things. You now have an in-house method. It's usually always based on something. As we're getting into the world where new and exciting emerging substances are coming along, you'll find you're getting a lot more new methods coming through that aren't based on initial standards, because we're operating at particularly some of the EQS level stuff at really the cutting edge of what isn't out there and available. So methods will be validated. So in soils, and I appreciate I'm talking to people in Scotland, so this might not be anything that you care about, is MCERTS, which is the Environment Agency Additional Quality Standard for Soils, is also applicable to other areas, waters in specific contexts, stack sampling, general sampling, a few of the bits and pieces, but from our perspective, it's soils, where we'll have specific requirements in order to determine what your limit of detection is, your reporting values. Lots of confusion in the world about the difference between limits of detection and limits of quantification, particularly as most people will misuse limit of detection when they really mean limit of quantification, and I've been guilty of it just as much as everybody else. And we measure analytical precision and bias, and if we've got time at the end, which we probably won't have because I've already been nattering for 35 minutes, in the quality section we can talk a little bit more about those. Participation in proficiency testing schemes, so people out there in the world who will generate samples of known concentrations of particular compounds, will send them out blind to any labs who participate in the scheme, and then we submit the results back, and the results are assessed across all the competing labs, participating, not competing, sorry, competing labs, and then you're assessed on a sort of pass-fail criteria of how well you've performed. And the participation and successful participation in these schemes is a crucial element of accreditation. Effectively, if a scheme is available for that and you cannot demonstrate participation and actually getting the right results out of it, then UCAS will be coming in have words and potentially removing any accreditation you have for that test. Some of the more commonly requested things that we do, so key contaminants and asbestos, the ever-present and generally actually ever-present. metals, the heavy metals, arsenic, cadmium, chromium, copper, lead, mercury, nickel, selenium, zinc, boron, beryllium, things adding in for your clear metals, chromium-6, which is becoming more and more commonly used as sort of an environmental quality standard. In organics testing, cyanide, sulfides rather. Phenols is a funny one because it's an organic compound, but if you're looking at monohydric phenols, it's typically done via an inorganic laboratory technique, i.e. colorimetrically. Just one of the dichotomies of lab life, and organic matter, and then for your organics, volatiles, semi-volatiles, so your pHs, phenols, chlorinated phenols, SVOCs, and total petroleum hydrocarbons. Sample prep. So we receive your tub of sample, or your tub, your jar, your vial, any combination thereof. Any samples that be analysed as received, so volatile organics, we will homogenise the sample as best as possible, and then we will take an aliquot of that to be run, processed and analysed. Everything else that can be done dry, we will take, again, we will potentially getting 1 to 2 kilograms worth of soils. We will take as a representative a sample as we can from that material. We will dry it at less than 30 degrees because it has to be less than 30 to be compliant with MCerts, and then we will crush and homogenize that sample by mixing, typically to a particle size of less than 250 micron. There are different variations we can adopt within this depending on what people want, but as standard, you would sieve to remove large inert material, and then stones, glass, bits of stuff over a 10 mil, but some standards require it too. There's a lot of flexibility. If you've got a particular requirement for a project, speak to the lab. They will be able to adjust and amend this process as needed. So what kind of volumes do we actually use for the testing? So weirdly, some of the more simple things require the most amount of soil material. So for pH, again, this one's a bit I2 specific, but will be broadly similar across any labs. You need about 20 grams. Metals, 1, VOCs, 5, SVOCs, TPHs, PHs, SVOCs, 2 grams. A lot of the low-level organics methods, you're looking at 1 or less than 1 gram. Now, if you try and think about that in terms of a total sample size reduction, if you're out on site, you have a field, a stockpile, you have tons and tons and tons of material potentially to test. That is reduced down to a series of small plastic and glass jars. We will then further shrink that down to, so for the look at SVOCs, 2 grams worth of soil. If you go through the actual analytical process, that ultimately becomes about 5 microliters of what you're testing for, suspended in an organic solvent, which then goes into an instrument. So you're taking tons to 5 microliters. But in terms of actual sample size reduction, the last stage is that 2 grams, but you're still going from tons to 2 grams. And there's got to be an understanding of the inherent uncertainty that that represents. I'm not quite sure what can be done about this one. Lab work is one of the few things where you can actually put a number on the uncertainty of measurements. By monitoring ongoing quality control standards, we can measure precision bias levels, again, all to follow, and we can put an uncertainty measurement on there. And you can give you basically a percentage value, which can say, generally speaking, operating at this level, this method will be providing results plus or minus a certain percentage, which is great and gets jumped on quite a lot because it's one of the few areas of the whole sampling to analysis process where you can do that. The only way ultimately to mitigate for any of this is one that most people's clients will not like, which is ultimately to take more samples. The more samples that you do, the more chance you are making sure that you are taking, you're getting a decent view of the wider material that you're looking at. So how does analysis work? And this is a broad simplification, but there are 4 bits of it. So you have extraction. So we've got soil. We don't really care about soil. We care about benzoate pyrene. How do I get benzoate pyrene out of soil so I can measure it? I don't, when I take that out of the soil, I don't just get that. I get the 15 other pHs plus several hundred other speciated pHs and non-US EPA 16 ones. So how do I distinguish between them? Once I've distinguished between it, how do I actually identify it and confirm how much is there? And then how do I figure out that back to what that represents in terms of the concentration in the soil? So we're going to look at a few different groups. So start off with metals. That is a picture of a plasma torch, which is part of an ICP. Just looks a bit flash. So majority of metals work is done by a technique called ICP, which is inductively coupled plasma. So in order to extract the metals from soil, we will use an acid digest. Now, varying different acids are used in this depending on the context to which you're looking at. So for things like looking at topsoil standards, you are looking at plant available nutrients, and you may do a weaker acid digest because you're just looking at the metals that are present in there that are likely to be absorbed into plant roots. For marine sediment work, you may look at nitric acid digests. Routinely, as to be considered the total soil, we'll use aqua regia, which is fairly common amongst labs. If you genuinely want a total, you can go up and start using things like hydrofluoric acid. And that is sometimes used in some of air monitoring and also certain types of marine monitoring. But for routine contaminated land, we tend to step away from it. And no other reason that it creates dead people. It's not very nice to use, and it's not very good for you. You can use you can use a microwave extract. Ultimately, the premise is you're mixing that with acid, you're applying heat, and that acid will then break down any of the metals that are present in any form within that soil, reducing them into a state where they can be then tested on the instrument. We use either ICP-OES, so optical emission spectroscopy, or MS for mass spectroscopy. Ultimately, you pass your extracted material through a plasma torch at bloody hot degrees. They will break down and decompose, and then we can either, for optical emissions, as they decompose, they emit specific characteristic wavelengths of light, or for MS, then you will get particular mass-ion ratios that you can identify as being characteristic to that metal. We measure them against sort of calibrated standards, so we have, we know if you put this much in, we get a response at this level. If we now get a response at this level, measure it up against the graph. Okay, well, that's how much we've got. Luckily, computers do a lot of this these days, so we end up with a lot of plots on computer screens and using the power of calculus, and luckily not everyone having to do it manually anymore. We can interpret under the area graphs to give you an indication of the strength of that signal, which is then directly equatable to the concentration in the soil, water, whatever your matrix may be. Organics, similarly, there is an extraction process. We will use varying different solvents depending on the polarity of the compounds you're interested in and the polarity of the solvents. Very common to use DCM, dichloromethane, just because it's a very, very good solvent, will extract an awful lot of things. But we do use in some cases acetone, hexane, and mixtures of all three, just to make sure we're getting a complete extraction process, be it either for soils, liquid extraction, solid phase extraction, direct injection. Some things are direct, solvent, bio. There's lots of permutations, but the basic premise is all you're using something in which the chemicals of interest are more soluble. They're happy enough in the soil, you put them next to some DCM. I'm going to go into the DCM. There's always certain phases of cleaning up and reconcentration, because ultimately you're going to get down to that 5 microliters in a little vial. We, wherever possible, will look to remove any potential interferences from there. We then use chromatographic techniques, LC, GC, things like TPH and pHs. We're using gas chromatography. So that 5 microliters is injected into an instrument, basically vaporized at about 350 degrees, and then injected into a 0.25 micron diameter silicon column. And as that is passed through under an inert gas under varying different temperature ranges, all those pHs, so we then go back to us thinking I'm trying to just find benzoate-pyrene, they're in a big lump at the moment. But as they pass through that column, they start to spread. That uses varying different types. Some of it's chemical interactions, some is based on size. But probably the easiest analogy is, imagine you have a long, thin corridor with a door at each end. And you've got a grown-up and a very small child. But in that corridor, it's full of people. You put them both in the door at the same time, the little kid is going to be able to dart through people's legs and get to the end quicker, whereas the grown-up is going to have to basically elbow the way through. Their passage through that is slower. So they may go in to the door at the same time, they will exit at the back door at different times. And that is a very, very basic analogy of size exclusion chromatography. If you start looking at different other types of chromatography, instead of people, it's different sticky things that people stick to. Anyway, that's another half hour in itself. We then move on to the detection. So you're looking at mass spectrometry again, flame ionization detectors, which is typically used for things like TPH, was historically used for PAHs, and UV, so ultraviolet lights. And what you end up is, as hopefully quite a lot of you, if not all, will have had visibility of things like this before. This is a chromatograph from a PAH run. So each of those peaks represents the presence of a compound. Now we will use, this is from an MS, so we can look at the mass spectral data that sits underneath that as to identify and confirm that it is what we think it is, and then we use the area under the peak to try and work out how much of it there is. Just to make me feel old, when I first started doing this, we're just coming to the end of the period where anyone who's ever seen a sort of Hollywood film where they're doing the lie detector test and they've got that constantly streaming roll of paper with a little wobbly needle, that was the output for these instruments. And it would draw all these peaks, it would draw on the paper, and then they would take that paper off and they would cut them out and they would weigh them. And that's how, rather than trying to mathematically calculate areas on the peaks, they would use the mass of the paper itself to indicate the size of the peak, and that ratio would then be fed back against a calibration to give you an idea of the quantity of results. We now use computers. Life is better. Inorganics analysis, apologies if there's any inorganic chemists on the call, is variations on theme of mix it together and see what colour it goes. They have very different common techniques. So things like pH, conductivity can be done by electrochemical, so monitoring electrical resistance resistivity by inserting probes. A lot of this, what we do is colorimetric, which is basically to say that there will be a series of preparatory steps and the compound of interest will react in a certain way or form certain complex compounds with the reagents you're adding and form a characteristic colour. It may not be a visible colour, it may be that it will either absorb or emit light at a particular wavelength. Some things, again, it was probably only about 10-15 years ago that chromium-6 could be done by effectively using something very closely akin to the Dulux paint colour chart. Based on the degree of purple to which the sample turned after you mixed it, would give you an indication of the concentration of chromium-6 in your sample. Again, we use more advanced techniques there, but the principle is effectively the same. So, I mean, this is just an indication of a basic spectrophotometer. So you have a light source, you have a Fujit, which will then basically ensure that you are transmitting, in this case, a particular wavelength of light through your sample. If the compounds you're interested in are present, they will absorb that light. There are other versions of this where in a reaction they will emit certain types of light. This is UV absorbance, there are UV fluorescence, diode array, lots of different variations, but basically it's using a very, very similar principle and then a detector just to determine how much of that light has passed through or been absorbed by the sample. Oh, hang on, didn't mean to do that. There we go. Lastly, I think a quick look at asbestos. Again, I could spend hours doing this now. I know everyone's got real jobs to do. So we're looking at visual inspection removal. This is a massive simplification of the process, but visual removal of large ACMs, fibre bundles, and then a subsample of that material will be taken, dried, and run through stereo microscopy looking for individual fibres. Again, the process of how to do this is fixed, but there are variations between labs and they tend to equate to the volume of sample which is used through the stereo microscopy stage. If in doubt, speak to your lab and they'll be able to give you some more details. little bit of a flow chart through on this one, as this one's I2 specific, but again will be similar, of where you've got an ID stage, you've got what's referred to as the stage 2 gravimetric quantification, which is sometimes some labs will split that into a gravimetric and detailed gravimetric quantification, and then you've got free fiber analysis by phase contrast optical microscopy, and it's all about which is the most appropriate technique for identifying the types of fibers that are present in your soil at the level of concentration in which they're present. But again, the lab should be able to advise on that one, depending on the samples that you're looking at. Just thrown in at the end here, just a few common issues that crop up and of reasons why we ultimately have to call people and give them bad news. So a lot of inorganic stuff that we do is colorimetric. So ultimately, we're depending on a reaction in there which will form some form of color-based reaction. So if you have in waters a high turbidity, this could interact, this could cause absorbance of light for different reasons other than the presence of the material that we're looking for. If you've got a coloured sample, if you've got coloration of the extract, there may be other materials in there that will react in a very, very similar way. For example, chromium-6, the reagents you're putting in, using it to form a complex with any of the hexavalent chromium that's present in there to create a coloured complex, but there are other metals and other things in there which will form very similar coloured complexes if present in above certain concentrations. So there are potential for interferences. Pretty much all methods will have some degree of interference, and it is pretty much a case of trying to find the most appropriate fit for purpose technique, bearing in mind that this comes with a cost. So analysis of chromium-6 is it's £3, £5, something like that. You're in the lower end of testing range. I imagine most labs will quite happily go away and develop the world's greatest chromium-6 method and charge you £2,000 a sample, but you're not going to want to pay for it. If you're paying £3 a sample, you have to be prepared that there are going to be potentially issues with it, because it's about getting the appropriate and fit for purpose test. Organics, generally, unless you're looking for oils and looking to do sort of TPH product identification, the presence of oil is going to cause problems with the ability to analyze for routine organics. Weird things. If you think that some of the tests are based on water extractions, based on the standards pH, we have to mix any soils with a 2.5:1 ratio of water. If your solid material is particularly absorbent and sucks up all the water, the analysis will fail. This is not thing, we can't suddenly go, all right, we'll just stuck an extra 10 mils in, because that means we're deviating from the methodology and no longer following the practice. So we follow the methods, and if there's something that is it's different from deviations, but there's something inherent with that sample material that's going to cause a problem, it's going to potentially result in an ability to report a result. General homogeneity, and more importantly, the lack thereof in samples, causes, particularly in solids, issues. As an example, I don't know if anybody's worked with incinerator bottom ash in the past. Did quite a lot of work with this in a previous life. The standard as written now for testing this material is you test every sample 11 times for metals, because of the inconsistency that you tend to find in getting results out. Because you can have 10 samples that are absolutely fine, and then one, despite it being incinerated and being prepped down to a very small particle size, will have a little teeny tiny piece of copper wire in it. That is not indicative of a high copper concentration across the whole material. It's just it's indicative that it's present in that one small part. So you do lots of repeat tests in order to give a good indication of what the wider material is like. In an ideal world where money is no option, we'd test every sample multiple times, and you'd have a plethora of data, and it'd give you a lot bigger model to work on. But obviously appreciate there are costs to work to, and there are clients who don't want to pay for things. But it's important for working from sampling all the way down that we, at all points, we're trying to get as representative a subsample as possible, but that is not always easy, or in some cases feasible. That, unless anybody's got another hour to spare to talk about quality, is a very, not quite as quick as I hoped it would be, whistle-stop tour of laboratory practice. Thank you very much.
That's brilliant, Will. Thank you very much. And as having started out my career in analytical chemistry, I loved all your stories. I could relate to a lot of the old style ways of doing things. And I did put in the chat that I think my best one was an iron brew bottle with a drinking water sample in it. And you opened it and all you could smell was iron brew. So yeah.
I was tempted to try and put that in somewhere, but I didn't know whether that would be sort of racial profiling in Scotland by as an example.
I've done it for you because it did actually happen. So I'm just going to stop the recording there just now so we can just do the questions.